Well, so in this course, the first module is electromagnetic field theory. The second module is transmission line theory. So this in the transmission line theory, we have first started with the concepts of the wave propagation in the transmission line, and then we have moved the definition of the wave propagation inside the transmission line by means of parameters called alpha, beta, and the characteristics impedance z naught, like that. So we are going to extend the study in terms of the other aspects of the wave propagation. That is nothing but the impedance and the reflection coefficients. We already discussed about that when in a air medium or in a different dielectric mediums, when there are two mediums, like one is having epsilon r1 and mu r1, and second medium has epsilon r2 and mu r2. When the wave is actually traveling and taking an incident on the boundary, there is a possibility of reflection, and there is a transmission which takes place. So we call that as a incident wave, and the reflected one as a the VR, and the transmitted one as VT. Okay. So we already discussed about the relationship between them. They are happening purely based on the impedance of them, so which is referred with eta 1 and eta 2. So the same thing happening in the transmission line with not a different one, almost very similar behavior. Okay. So where actually we have studied about the reflection coefficient, and the reflection coefficient is nothing but eta 2 minus eta 1 divided by eta 2 plus eta 1. So I think recently you have also performed in CAT 2 as well. So you people very much familiar with that. The same concept is actually happening in the uh, so-called transmission line also. So we are going to study those aspects, and ultimately our main important objective is to make this reflection coefficient 0. So there is only one possibility, that numerator is supposed to be 0. So how it is possible? When both the impedances are same. And in case of the mediums, it is possible by having this values like epsilon or mu or these values supposed to be same. So that is how it can happen in the real mediums. But in case of transmission lines, there are interesting facts can be adopted to make this reflection coefficient as equal to 0. Then only we can say that the wave will travel from one medium to another medium maximum. Otherwise, from one transmission line to another transmission line, maximum transmission could be possible, and we can avoid the reflections. There are some problems with the reflections we will discuss over the course. Yeah. So this wave propagation we discussed, and this the wave propagation always defined with important parameters like alpha and beta. They are defining the attenuation as well as the phase of the propagation, and the same thing happens inside the transmission lines also. So that is what we have defined as propagation constant with phase constant and attenuation constant. This, when we compared with waveguides, we will clearly see the behaviors. And now, keeping that in mind, we have started the transmission line theory. The transmission lines, these are the important transmission lines. Other than that, we have one more thing, which is not shown here, is waveguide. Okay, so all these four are nothing but important transmission lines. These transmission lines especially used for high frequency applications. There are other wires, single wires or two wires or multiple wires can be used for electrical power transfer, but the completely here the concept is completely different. There actually the frequency is very, very low. Can anyone say that in electrical circuits, what is the maximum frequency of operation you have heard about? What is the normal frequency you hear about in case of electrical circuits like motors or mm, or any other home appliances? Can you can you tell the value, approximate value of frequency? No idea. Okay, so to your home, what frequency signal is coming? Electrical signal is coming. Do you know that?
50 to 60 hertz.
Great. Yeah, 50 to 60 hertz only it is coming. So this is actually in this particular frequency, the wave is actually moving at very slow phase, and there is no concept of beta as well as this so-called the impedance, which we call impedance. That is not at all required. Only resistance is more than sufficient. Rarely phase difference is coming. That is compensated by this three-line theory called phase, and then three phases we are actually bringing into the picture. So by the way, they can easily solve many of the problems. But in case of the high frequency transmission lines, they are having different properties, like they will be size will be very narrow, because they are supposed to carry very high frequencies. So their dimensions will be approximately with respect to the sizes of the lambda of them. So when we compare the frequency in gigahertz or megahertz, this wavelength will be in terms of millimeter size. So that is why microwave circuits also referred as millimeter waves. So these all dimensions will be in millimeters. Of course, the waveguide also will be in millimeters. So inside that, how the wave actually travels. So that is what the whole theory is all about. And we can't always use the electric and magnetic field to define that, because ultimately the use is we have to connect with electrical circuits like electronic circuits like transmitter, receiver, two telephone cable, two telephones we have to connect, or we have to connect the transmitter with the antenna for a mobile tower or with the mobile phone, like that. So where the transmission line is often used. So that is why we are converting this transmission line field components into alpha, beta, and the characteristics impedance. Now we are going for next level. We are going to define them as impedances. So that is what the whole class is all about. So we already discussed why this transmission line theory is required with this particular way. It is because during about 100 years before itself, many experts they have mentioned, including Hertz as well as J.C. Bose. Many people describe that when the wave is traveling in a wire, it gives completely different resistive behavior, and so this resistive behavior gives reflections in the backward directions, and that is why maximum power is not going from the transmitter to the receiver. The maximum power is not going. Okay, and moreover there is a delay taking place. So from here to here, at velocity of light, when it travels, it's supposed to reach in a particular time, let's say at time t1, but it is coming at very slow phase. So there is a great link between this wave propagation and the phase delay, as well as the reflection what is taking place at this at the transmitter side, at the receiver side, all these things. So this is a very important puzzle at that time, and this was originally solved by Oliver Heaviside. In fact, he was assumed as non-Maxwellian, like people who don't believe in Maxwell's equations and they try to find the equations are wrong. And Heaviside is one of the person. He was very great mathematician, and he's supposed to prove the Maxwell's equation, particularly the displacement current. All these concepts he want to prove wrong. But nearly about in his notebook itself, he mentioned that he derived around some 21 theorems. All these 21 theorems become correct with respect to Maxwell's equations, and in fact that same theory itself helpful for proving the concepts correct. So and quoting this particular one only, we can say that a particular theory is self-consistent or complete theory or not. Okay, and for instance, Einstein also mentioned Oliver Heaviside's description about the completeness of the theory to describe the quantum mechanical theory is not a complete one. It needs some other physics descriptions from the other theories like electromagnetic theory or um, other fundamental theories, including optics. All these things required to describe the quantum states of the materials. So that is why he said it is not a complete one. So Oliver Heaviside is that much genius. That is what the end thing. So this is how the whole theory started. So the ultimate objective is, if you can define the impedance at any particular point, then you can easily get the overall input impedance of the circuit. If the input impedance of the circuit is got, then for a particular frequency you can easily say that when this impedance will be same, so that the maximum power will go from here to here, because this distance is not in millimeter scale or centimeter scale. This sometimes will go in kilometer size, sometimes it will go in meter size. And interestingly, nowadays the circuit, this transmission line used in the very small size, that in mobile phones also it is used. In mobile phone we have a transmitter chip and you have a PCB board. On this top it is soldered, is it? So another antenna might be here. So from here to here your transmission line is supposed to carry, and we have a ground plane here in the bottom. So the wave actually travels from this transmitter to the antenna, and the antenna is supposed to radiate the signal outside. And this antenna will be having some different impedance, which we call load impedance. This is having some other impedance called, let's say, source impedance. And this transmission line has its own characteristics impedance. Now we have to bridge all of them. And so then only we can make the power transfer from the transmitter to the antenna maximum. Then only the antenna can radiate the maximum power and it will go for a long distance. So this is the very interesting as well as critical problem in terms of so-called the communication systems. So where this particular theory solves greatly. So that is why the transmission lines are modeled into RLC equivalents. The benefit of it is we can describe all of them into very same wave equations. This already we discussed, and these all wave propagations are defined in terms of the traditional alpha beta concepts like attenuation constant and phase constants. And later it also described the characteristics impedance or wave impedance of the transmission line. So this is very interestingly, they are actually beautifully, the equations were being arranged so that actually many people think actually like E equal to mc square, like that. In case of electromagnetic theory, this particular equation often been sounds very easy to remember. So you will get this characteristics impedance, and so now we got the overall three important parameters like alpha, beta, and the characteristics impedance. So that is why if you see the transmission line theory, any notebook, if you see that they will draw the transmission line as a two line, and then they will mention alpha, beta, and then Z0. This three value will be put in a bracket, and inside the two lines it will be kept, not in the top, not in the bottom, exactly in the middle. So which means that within this starting point to end point, if there is a transmission line, and the wave will propagate in this, and this can be described by this three properties. This primary two properties like alpha, beta, secondary property like impedance, everything can be described by this. And this alpha, beta, is that not, this three can be described by this RLGC. So we can define in terms of alpha, beta, Z0 or in terms of RLGC. And you should remember that these RLGCs, all the values are described in terms of the corresponding ohm per meter or Henry per meter or Siemens per meter or Farad per meter, like that it will be defined. So this is the important thing you have to notice in the transmission line theory. And there are some special cases in the transmission lines, lossless transmission line. Of course, it is almost impossible that the attenuation is supposed to be zero, which can be possible by having this the resistance and the conductance supposed to be zero. Okay, so this is possible when you have the two wires or completely almost like a superconductor where the conductivity is infinite. So we will get this condition, and there are some interesting advantages that the impedance will become root of L and C. So R and G value is gone. So this is why the impedance will be mentioned as a purely reactive one, and this is very advantageous one. In fact, you will get the velocity also quite same as that of the regular velocity what is there in the air medium. And the other one is the distortionless line. I already discussed about that. That when the wave is actually in a transmission line, and I am sending from, let's say, transmitter to receiver. I'm sending information. This information is actually sent into different frequency component, F1, F2, F3, which we call broadband. So when this all signals are traveling, each and every signal will be having its own wave velocity, and because of that, their arrival time will be different. If the arrival time is different, then the transmitter is supposed to wait for a while to get all the signal. So this is we call coherence time in the communication systems. People used to say this. So this coherence time increases, the speed of the communication will always go down, and there is a possibility of error as well. So in order to solve that, Maxwell was a greatly genius. He was having this problem already identified and had a solution for that. When the problem comes, he simply revealed it, and that concept can be done by R by L equal to G by C. When you substitute in the wave propagation, you will see that this value will bring alpha and beta, particularly beta will come linear with respect to frequency. So this frequency will be having u, this also will be having same u value since they are linearly related. So when the frequency increases, the phase velocity will be quite same. All the wave will travel in the same delay and will reach the receiver in the same time. Because of that, the clashing between the frequency components also will be solved. So this is what the expected one for the distortionless line. And if you calculate the alpha and beta for any transmission line, if this behavior is quite like this, it is very much useful. For instance, if you take a rectangular waveguide, it is having linearity of gamma, that is the phase beta. This beta is linear here. So this is what we expect, and here only it can be used as a transmission line. So here it cannot propagate, and after that it will start to saturate. So here also linearity can be maintained. So this is we call useful region. Interestingly, if you take a PCB which is having a conductor in the top, bottom, ground plane, where if you connect the transmitter and receiver here, or antenna and the transmitter, or receiver and antenna, so you will see that the beta is almost constantly increasing with respect to this frequency. So this is why this particular transmission line, planar transmission line, often referred as universal transmission line, can be used for almost all the frequencies, from low frequencies and then microwave frequencies, and then here it is keep on going. And even recently I have seen that in terahertz also people are using the same type of planar transmission lines they are using. In fact, in mobile phone, even if you adapt mobile phones for 5G applications, which are going to work in 38 or 67 or 67 to 70 gigahertz, it is going to operate with the same type of transmission line. So it is very much important to understand this concepts for almost all frequency range of communications. Here it is the summary. We have seen this example for a given transmission line of a particular characteristics impedance and a beta value, how to calculate this secondary components like RL, GC, and then alpha, beta, all the values, how to calculate. Alpha is already 0, beta is given. So, and this AR line means the two wires are kept in AR medium. So obviously there won't be any conductivity. G will be equal to 0 naturally. Resistance also will be assumed as 0. Okay. In fact, there is no information about that. So naturally we can take it. Alpha equal to 0, beta is given, and Z0 naturally will become reactive. So you will get root LC. Now when you multiply this, you will get L. When you divide, you will get C. So that is how L and C values are calculated. Now we got all the values R, L, GC. So that is what expected in the question. Another example here you can see, but this is actually come up with alpha, and the phase velocity is given. The phase velocity is indirectly they are giving the beta. So alpha, beta, Z0. Now for this 3 you have to calculate this RLGC. Already we discussed about that. There are some exercise problems are there. So just try these things. Now we are coming to the main problem, that this primary and secondary parameters supposed to be defining the impedance of the transmission line. So why this impedance supposed to be defined? Because this impedance will tell the maximum power supposed to be transferred from here to here. And we already have discussed that this is assume that this is medium 1 and this is medium 2 and this is medium 3, and this medium has the impedance of ZS, that is the source impedance, and this is having load impedance, this is having the characteristics impedance. So this 3 impedance supposed to be linked. Okay, so then only we will get the maximum power transfer from the source to the transmission line, and it will propagate, and from here to here it will travel, it will go. So in order to make this link, we supposed to need this reflection coefficient supposed to be 0 at the desired frequencies. If your communication is taking place at 2 gigahertz, then at 2 gigahertz we need the reflection coefficient supposed to be 0, because the reflection coefficient, if it is high, it will be reflected back. So the effective power transmitted is the remaining power of the reflected one. I am giving 10 watt power, at least 9 or 8 watt power supposed to be reaching at the load or the receiver side. Then only is the best transmission. The remaining power may be reflected back, but this reflected one will go and reduce the effective power of the source, which often referred in many of the engineering, even VLSI, embedded system, and then basic electronic theories, as well as microengineering, which we often refer as source degradation. Okay, this source degradation, one of the important sources is reflection also. So it is best to have the reflection as low as possible. One more thing, that the reflected component will be reflected again and again. So this reflected signal will accumulate at this particular point, will heat up the junction point between these two transmission line and the receiver, and here also there could be a possibility of accumulation of the power. So this may break the chain also. So this sometimes happen. Let's say your mobile phone is short circuited by some water or something, then that is some reason that actually mobile phone is not working, or some mobile phones are having sensitivity about this reflection. When the reflection is very high, it will automatically terminate the battery, and the mobile phone will go to safe mode. Okay, so these are the important issues. So it is the best thing is we have to calculate the impedance of the wire at any particular point. So how to do that? For this, we supposed to know what is mean by impedance. So impedance is nothing but the complex ratio of the voltage and the currents at any particular terminal point of the given circuit. So this can be calculated by integrating the electric and magnetic field powers, so that we can very well use the Poynting vector to calculate the power. This power is divided into 3. One is the magnetic energy, electric energy, and the power dissipated from the this is the power dissipated from the circuit. So this is what going to be the resistive one, and this Wm is going to be capacitive, and this one going to be inductive. Okay. So that is what is giving the rise to the meaning of the so-called the input impedance. So the input impedance is nothing but complex ratio of voltage and resistance, which has the real part as the resistor and the imaginary part as the reactance. So this we can multiply with conjugate, and here as well as, sorry, here is I star, here also I star. So this will give I square, this is Vi, and this is nothing but power, the denominator I square you have. So now this ratios are nothing but the impedances. So this will give the resistance, and this one will give the reactance X. This reactance X can be capacitive or inductive. Sometimes combination of both could be possible. Okay, so this is how we can define the impedance at any particular point in the circuit or at the input side. And when you define at the input side, we will call that as the input impedance. Similarly, if you mention that in the load side, you will be calling that as a load impedance, like that. Now for a transmission line, we have to calculate this impedances. Okay, so in order to do that, we are supposed to make a clear statement that we are having a source and a load, and both are connected by a transmission line of length L. So in order to define the transmission line, you should always be very clear, and in fact you should be professional enough to define properly whenever you are drawing the transmission line, that you have to mention alpha, beta, and the Z0 value. You can see that it is defined here. And instead of alpha and beta, they simply mentioned as gamma. It indirectly means alpha and beta only. Okay. So I expect you to write alpha, beta, and Z0 value. And the length of the transmission line is given at z equal to 0. That is the along the z axis, z equal to 0, source is connected. And here at the length L, at the end of the length L, that is z equal to L, we have a load. Okay, the load has the impedance of load impedance, and the source has the impedance of source impedance. Sorry, ZS. Okay, now from the ZS, from the VG, that is the generator, and it can be, most probably it is a high frequency source. We can call it as a transmitter, or this is the received antenna. From the received antenna, after a transmission line, it is going to the receiver, or from the transmitter, we are actually connecting to the transmission line, or between the two chips, anything you can describe, but this is a general statement. Okay, so this VG is going to generate a voltage signal, and as well as corresponding voltage will give the current as well. So this wave is actually supposed to travel, and according to the basic wave theory, whenever there is the existence of incident wave, we call it as a plus one. There is the existence of the reflected one, we call that as a V minus. Okay, and now we have to define with respect to different locations, and that is what it is described here. We already know about that because in the very beginning itself we described that. I believe you can still remember that here. Yeah, here we already described that the wave whichever is traveling at any particular location can be defined by the incident and reflected component. Incident wave will travel in the positive Z, and the reflected component will travel in the negative Z. Well, so we got the voltage and current terms. We're supposed to be very careful about defining this voltage and current. The voltage is simply almost don't have any sign to describe the travel direction. So that is why you can see that the a voltage at any particular point is nothing but sum of the forward going signal and the revert the backward signal. So this is the incident wave or reflected wave, both at any particular z points. Okay, and that is given by sum of that. But in case of the current always has its own direction. So to describe that, the wave is traveling in the forward direction is given by V naught by Z naught. It is like V by R. So V naught by that, and the same exponential term is coming, but this negative indicate that it is traveling in the backward direction. So this is the very important difference between the voltage signal and the current signal, which is traveling in both forward and backward direction. And at any particular point, you have to add this both incident and reflected component, or forward going signal and the reverse going signal. Then only you will get the total potential at any particular point. Now we are going to characterize the V naught and I naught, which is nothing but the incident and the reflected component at the z equal to 0 point. That is at this particular point. So how to do that? We are going to say z equal to 0. So when you substitute z equal to 0 in this two equation, then you will get this term will go 1, this term will go 1, everything will go 1, and you will get all the voltage terms. Now we can easily calculate this incident and reflected component, because just we have to rearrange this equation. So how to do that? Just you multiply this entire equation with Z0. So this Z0 will be cancelled. Now when you add, you will get V0. When you subtract, you will get V0 minus, V0 plus will come, V0 minus will come when you subtract. I believe you can easily understand the mathematics behind that. But when you do that, you will get 2 times. So that is why in the denominator you have 2. So 2 V0 is nothing but V0 plus Z0 I0. And this, where what is this I0 is nothing but the voltage, the total voltage, which is sum of both the incident and reflected component at z equal to 0. Otherwise, this is the voltage and current generated by the source. So this can be easily calculated using this simple well-known expression. So which is nothing but voltage division formula only applied here, where Z0 is Z in essence but input impedance of the transmission line, what we see from here. So this clearly indicate that how the voltage and current. So when you substitute these two expressions here, you can easily calculate the incident and reflected components. Now we calculated at Z equal to 0, that is at the source side. The same expression can be calculated at the load side. So at the load side, we have Z equal to L. So we are going to substitute Z equal to L. When you substitute that, the same expression similar to here, you will get here. But here you got in terms of V0. V0 is nothing but the voltage and current at the source side. Here we have at the load side, we call them as VL and IL. Okay. So you should remember that this VL and IL, they don't have any source like that. It is possible by the wave supposed to travel up to here, and when it is going back, this potential and current will be created. So VL, IL is defined, and when we substitute that, we got it. So this is the voltage and current. Now we are going to calculate the input impedance. So how to calculate the input impedance at any particular point in the location? So this is the Z equal to 0 point. This is Z equal to L point. At any particular point, if we say that the location Z, now we should be in a position to calculate the impedance, input impedance we are supposed to calculate. So what is the advantage of that? Whenever we scale the transmission line, we can easily predict the total input impedance, and the input impedance can be matched with the source so that the maximum power will be transmitted at the input side. Same thing we can do at the load side very easily. So how to do that? We have to calculate the input impedance, which is nothing but complex ratio of voltage and current at location Z. So at location Z, it can be nothing but sum of the incident and reflected component divided by difference between them. This we already know about that because this is how it is defined. Thus we are going to add and subtract. So you will get this two descriptions. Now we have to substitute this values V0 plus, V0 minus. We already calculated V0 plus here. So these two equations we are going to substitute here, and when you substitute, you will easily calculate the one. And now it is defined as from the length L, it is located at length. So that is how it is described. And to define the backward direction, it become plus. Normally we use minus, so that is the main difference. So this is the incident component, this is the reflected component. Both the components are substituted here in this equation. Now this equation will be resulting this. This is a kind of a little detailed derivation will be there, and that is not a big trouble. So what actually will happen when you substitute this VL, when the VL is adding, you will get this term will come like this: e power gamma L plus e power minus gamma L divided by e power gamma L, sorry, minus e power minus gamma L, like that will come. So this can be reduced as this hyperbolic functions, like the tan has gamma L we can substitute, because this is a very well-known identity. By reversing that, inverse of that, we can do that. So that is how it is rearranged, and we got this equation. For detailed derivation, you just go to book, it is available. Otherwise, the best recommendation is Microengineering by Poser. So in this book, it is available. But after that derivation, you are not going to get great knowledge about that. You will get once again the same equation. So that is why I'm to save the time I have given here. So this is the input impedance at any particular Z point or at any particular length. We can easily calculate that. So when the length increases, the impedance will keep on change. And interestingly, at certain length, you will get these all impedances will cancel each other. You will get only Z0. That also possible. So because this value, we can make it as a 1 by carefully selecting this L value as well, and carefully selecting the load impedance also. And we should remember that whenever this ZL equal to Z0, you will get the entire term will become 1, which means the input impedance equal to Z0. So that if the input impedance equal to Z0, which means that the maximum power can be transmitted from here to here. Okay. So this is the impedance of the transmission line. Once the impedance is calculated, now we can easily calculate the reflection coefficient. We already know what is reflection coefficient. Reflection coefficient is nothing but the between the two medium, how much power is reflected back out of the incident wave. So we will call that is the incident wave as the V plus and the reflected one as a V minus. So the reflection coefficient is nothing but V minus by V plus. Now we have to introduce this transmission line. So this transmission line is introduced with this two extra quantities like e power gamma L, and for backward wave e power minus gamma L is placed. So now this 2 will become e power 2 gamma L, and at the load side and the source side. So both sides we can easily get it. And when we calculate the magnitude alone, we will simply put gamma L is nothing but eta 2 minus eta 1 divided by eta 2 plus eta 1. So eta 2 is the load, eta 1 is the transmission line whose impedance is Z0. So both the values are substituted here. So this is the expression for the voltage reflection coefficient, because it is calculated out of the voltage. Similarly, current reflection coefficient also, that you will get the same magnitude only will come. So this is the load reflection coefficient, and from this we can easily calculate the overall reflection coefficient, which in other words the reflection coefficient at any particular point, because we know the input impedance. So obviously we can easily calculate the reflection coefficient. So this is nothing but Z in minus Z0 divided by Z in plus Z0. So that's all. We got the load side reflection coefficient, and the input, we often refer this value as the gamma in, which is nothing but input reflection coefficient. Okay. So by this we have defined the very important problem what we thought of describing. So at this source side, we will always, people used to do like this. So we have a transmission line whose alpha, beta, Z0 is known, and this is the starting point, sorry, 0, and this is the end point, and here we have connected a load. This load can be anything, but this is characterized as ZL. So this can be a telephone, this can be an antenna, this can be another transmission line, or this can be a chip, microwave chip. So it can be anything. So same thing happens here as well. This side we have a source. Now at this particular point, we are going to calculate the input impedance. So we already described that. And at this particular point, the input impedance is very much same as that of ZL itself. So now we know the link between this input impedance and ZL, because that is what first we derived. And at any particular point also we can easily calculate the input impedance with respect to the location Z. So by the same way, we can even define the input reflection coefficient and the load reflection coefficient. So either we can define this or define this. Now once this equations are arrived for a given condition, we can very well calculate how to make this value 0. So this equation suggests that you make the input impedance equal to Z0, then you will get both the value will become 0 and the reflection coefficient will become 0. And how to make the load reflection coefficient 0? We supposed to make the load impedance and characteristics impedance supposed to be equal. So what indirectly means that if you take a transmission line, you always try to make this ZS equal to Z0 and ZL equal to Z0. So here also Z0, here also Z0, here also Z0. So everywhere Z0. So maximum power will be transmitted to the maximum power will go from source to transmission line, and power will travel, and from here maximum power will be going, because there is no reflection, because the reflection coefficient equal to 0 here and the load reflection coefficient equal to 0. So this is the benefit of having this description like characteristics impedance or input impedance, or we can define as reflection coefficients. So that is what we have done so far now. So these equations can be used to define that. Now many people nowadays using this reflection coefficient. Some people they are using alternate description of the same reflection coefficient as standing wave ratio. So what is this is nothing but whenever there is a forward going wave, it reaches the load. Okay, so here this is Z equal to L location. We have some load. Okay. And this load is not matched properly, which means that this is not equal to Z0. Then what will happen? Reflection will take place. So due to the load reflection, the wave is reflected back, and the blue color line indicate the wave is traveling in the backward direction. When the forward wave and the reverse wave or the backward wave, when they meet each other at any particular point, we can calculate the voltage. Is it? So V is nothing but V plus and V minus. So the sum of that. Whenever the magnitudes are same, you will get maximum. Whenever the magnitudes are opposite, you will get minimum. Is it? So we can easily say that within the transmission line from load side, you will always see that at one particular point you will get maxima, at another point minima. Maxima, minima, maxima, minima, like that it will keep on come. So this is we call V max and V minimum, and this ratio, this magnitude ratio, V max by V minimum, often referred with the coefficient S called standing wave ratio. Okay, and combination of this wave, the resulting black color wave is nothing but standing wave, and this you can easily see that you just take a water and put a one stone here, another stone here. You will see that the wave will go in backward direction, and you will get some clumsy wave. So that is nothing but standing wave. The standing wave also you can see in the universe also, that is what makes the ripples, and people are saying that this ripples only made atom to planets and everything else. So this is the standing wave, and the standing wave alternatively can be represented by the reflection coefficient also. So this is the simple formula. So if you know the reflection coefficient, you can define S. Otherwise, you can also define the reflection coefficient as the function of S minus 1 divided by S plus 1. Like that also you can define that. So this is the this is how we can describe the wave propagation from source to transmission line to load. And by optimizing or by calculating the proper values, one can resolve the problem of reflection, and they can get the maximum power transfer from the source to load could be possible. Let us take a simple problem, and we will calculate the reflection coefficient, standing wave ratio, all these things. So here there is a lossless transmission line, therefore alpha equal to 0, and its characteristics impedance is given, which is 50 ohm, and the length is given, that is 30 meter long, and the frequency is given. Okay. So the line is terminated by a load impedance. So the load impedance is not simply resistive, it is having reactance also, and its phase velocity. So indirectly beta is given. So now we have to calculate the reflection coefficient, and then standing wave ratio, and the input impedance for the given transmission line. So how to calculate that? So first we will draw the transmission line, and here we have a load, and there is a source here, and so this is Z equal to 0 point, here Z equal to L point. L is given here as 30 meter, and the characteristics impedance alpha is given 0, so we need not to define that. So beta and the Z0 is given. So now we have to calculate the input impedance at this particular point, and load impedance is given, and the input reflection coefficient and the output reflection coefficient, and then standing wave ratio. These three things we have to calculate. So the reflection coefficient, most probably people refer the reflection coefficient as the load reflection coefficient. So which is nothing but ZL minus Z0 divided by ZL plus Z0. So we are going to substitute the ZL by Z0, and this is supposed to be 60. Something wrong here. Okay, so now in difference here the sum of them. So you got the value. Now this ratio will give two values. One is the magnitude, another one is the phase term. So what we see in here is the magnitude term. There will be a phase term also will come. The phase term is nothing but tan inverse of the reflected by the incident component. So we will calculate this value later. Now it is not an important one. Now then we are calculating the standing wave ratio using this simple formula. When you substitute that, you will get the value of 2. This value will be always greater than 1. Then using this phase velocity, we can calculate the beta. So from this, when you multiply with L, you will get the total phase difference created by the transmission line, which is often represented by this beta L. So beta L is also called electrical length. The physical length is 30 meter, but the electrical length is 120. Now we can calculate the input impedance. So what is the input impedance formula? Input impedance formula is nothing but Z0 into ZL plus Z0 tan H gamma L, where gamma is nothing but alpha plus j beta. Okay, when you put alpha equal to 0, this entire term will change. So this is the new expression for alpha equal to 0 case. This j term is introduced, this imaginary part is introduced, you can notice here. Otherwise it is simply same. The H is gone, the hyperbolic function is gone. Now we are going to substitute all the known values, Z0, ZL, and then beta L, which is already calculated here. So when you substitute here, you're supposed to properly multiply and divide. So you should not randomly do that. So my best advice is always do within the bracket, then you multiply at final. Don't quickly multiply and don't do like numerator denominator like that. You always keep this Z0 till the end. So simply apply the value, and when you use the calculator, you're supposed to be very, very careful, because you have to convert to the you have to use the modes properly. Either the theta means like the degree mode, or what do you call radians mode, like that. You're supposed to be very, very careful about that. And finally, you can easily multiply this, and you can get the magnitude of the impedance and the phase. Also, you can calculate as the real and imaginary part. This is the real term, this is the imaginary part. This is nothing but the input resistance plus J input reactance, which is nothing but Zn. So for a transmission line, once you defined this, nearly 90% problem is solved. Then we can we have to make some decisions how to make this impedance same, so that maximum power will be transmitted. In the future classes, we are going to see how to solve this problem. For instance, you can notice here that this load impedance is not at all equal to Z0. Not even the real value. Real value is 660 here. Here it is 50. Definitely they can't be matched. But there are some interesting concepts when you put the transmission line in a different way, so you can match it. So that is what we are going to see in the future class. So this theory, I believe you got the understanding. So I will stop here. The next class we will discuss about when we terminate with the short circuit. So what is meant by short circuit? We have to connect both this positive and negative wires short. So which means load impedance equal to 0. And open circuits, when both the transmission line, when there is no load, when the load is 0, that means the load impedance is equal to infinite. So that is called open circuited line, short circuited line. And these lines are largely useful for various purposes. And finally, we have a matched line where the reflection coefficient, the input impedance equal to Z0. The moment you put this, then you will get the input reflection coefficient will become 0, load reflection coefficient will become 0, and this also will come 1. So the interesting benefit is you will get the input reflection coefficient will become very, very low. This is actually given in dB scale. When you convert this value will come 10 power minus 8 will come. So this is approximately equal to 0. So this is what the normal expected behavior for a given antenna system or a given transmitter receiver. Everywhere else we want the reflection coefficient supposed to be close to 0 or very lowest possible value. Here you can see that the other frequency components are simply reflected back, okay, because the reflection coefficient is 0 dB is equal to 1. Okay, here also it is 1, which means all the power whichever is incident wave completely reflected back. So this is the benefit of the very important as well as very crucial interesting benefit. This been studied by 3 to 4 people. One of the important person is his name is J.L. Armstrong, I think. Actually, he's the one pointed out the importance of this particular diagram. You can notice that within this frequency range only, all the reflection means almost all the powers are going from source to load. Okay, but here it is all reflected. So where we can use this, we can use it for communication purpose. Only the person who is utilizing this frequency can enjoy the communication. Remaining all people cannot touch this frequency. So this is what made nowadays we can tune this by varactor diodes or all these things. So we will discuss about this much more in detail in the near future. So I will recall this theory again with other 2 more numerical problems. Then we will go to short circuited line, open circuited line, and the matched line. And we will have some interesting transmission line theories in the upcoming classes. Thank you all. Kindly see the recording again and